Our last example again is going to be really testing us on how well we understand total energy and it's being conserved at all points along the way. The key that we really have to note with these examples and what we've been doing in the review is we've been dealing with only frictionless. I haven't had to worry about any work lost to friction. Things become a little bit more complicated when you bring friction into play. You might remember that from Physics 20. But we don't deal with that same degree of energy type question in Physics 30. We got a lot of other things to deal with. So in this case, let's figure out what we have for total energy at the start, figure out what total energy we have at the end, and note that they're going to be equal. So the diagram shows a frictionless loop-to-loop track. Location A is 2.4 meters above the ground. So we're talking about A, we're going to say its height equals 2.4 meters. B, 1.1 meters. And C, 1.90 meters. We have the mass of the ball, 32 grams. I'm just going to write here in kilograms right off the bat. 32.0 times 10 to the negative 3. To change it to kilograms, proper units. And its velocity at A, it has an initial velocity of 2.50 meters per second. What we want to know is what will its velocity be at C. We don't really care about B in this question. Because it's frictionless, we should know that the total energy at A equals the total energy at B equals the total energy at C. It just may be in different forms at those points, but the total energies will be the same. So what I'm going to do is set up the formula. If I could find the kinetic energy at C, I could find its velocity at C. So let's think about this for a sec. Let's set up the total energy at A. At A, we have potential because we're above the ground. We have kinetic. So the potential energy, and I'm going to use a little subscript A, plus the kinetic energy at A, that's the total energy we have at A, is going to be equal to the total energy we have at C. Now at C, we have potential energy at C as well. Potential energy at C plus kinetic energy at C. Let's solve for the one thing we're missing. If I'm looking for velocity, that means I need kinetic energy. So let's move the potential energy at C to the other side. I'm going to do this equation in 2 steps. Total potential at A plus total kinetic at A minus potential at C is going to leave us with kinetic at C. Now let's put our formulas in. The potential energy at A will be mg, I'm going to go h at A, plus kinetic at A will be 1/2 mv, and I'm going to put v at A squared, just so I don't put the wrong velocities in, minus potential at C will be mg height at C equal to kinetic at C. I could put that formula in, but then it becomes pretty messy to work with. Let's just do a substitution of this formula, and then we'll go find from the answer the velocity. You can do this in one step, and by the way, you can do this using different formulas, but I'm using the formulas you have on your formula sheet for potential and kinetic. We have the mass, we have gravity, we have height at A. We have the mass, we have the velocity at A. We have the mass, we have the gravity, we have the height at C. We have all of those numbers. All we need to do is put them in. So I'm going to go to another slide because I don't have enough room to do that here. So we're going to go 32 times 10 to the 3 kilograms times 9.81 newtons per kilogram times the height at A was 2.40 meters. We're going to add 1/2 times 32 times 10 to the negative 3 kilograms times the velocity at A, which was 2.50 meters per second squared. And now we're going to subtract the mass. 32 times 10 to the negative 3 times 9.81 newtons per kilogram. And I'm just going to squeeze this in. The height at C was 1.90 meters. And that's going to be equal to, which I'll put on this side, the kinetic energy at C, what's left over. So it's the potential at A plus the kinetic at A minus the potential at C to give us kinetic at C. Now, if you're fairly good at algebra and factoring and simplifying, you could probably save yourself a little bit of work in terms of punching these numbers in. But sometimes I find that when students try to simplify, they end up making more mistakes than just punching it in. So I'm going to punch it in. .5 times 32 to the exponent negative 3 times 2.5 squared. Subtract 32 to the exponent negative 3 times 9.1 times 1.9. Should leave me with a kinetic energy, just to check as we go here, as 0.25696 joules. Once we know that, we also know that the energy kinetic at C is going to be equal to 1/2 mv at C squared. Manipulate that formula for velocity, so you'll multiply by 2 times the energy kinetic at C, divided by the mass, and then take the square root, will be equal to the velocity at C. So the velocity at C will be 2 times 0.25696 divided by 32 times 10 to the negative 3, and then take the square root of that whole thing. Well, I left that number on my calculator, so I'm just going to go times 2 divided by 32 to the exponent negative 3. End up with 16.06 before I take the square root. Take the square root of that answer, and you end up with the velocity at C, which works out to be, to the appropriate sig digs, 4.01 meters per second. And here you should do a quick think, or a little bit of thinking here, to check to make sure that this makes sense. If A is the highest point on this loop-to-loop, and it's traveling at 2.5 meters per second, if C's at a lower point, it better be traveling faster than faster than 2.50, and it is. Notice we don't care about the fact that it's gone through a loop and curves and all that stuff because it's frictionless. You know, roller coaster physics is all based on this kind of formula, but they also bring into the fact that you do have to account for friction. But on every roller coaster, or every loop-to-loop, the highest point has to be at the beginning, otherwise your object will never ever make all the loops. And that's why, due to the fact that we have all these losses along the way. It's all about energy conversion. What I want you guys to work on is practice the kinetic and potential and work formulas using the examples in exercise number 5.